Hi everyone, thank you for watching our presentation on dependency patterns of complex sentences and semantic disambiguation for abstract meaning representation parsing. In our paper, we present an initial solution to deal with complex sentences in AMR parsing. Let's start with background of our study. When speaking of syntax and semantics in general, it is assumed that semantic structures reflect syntactic information such that dependency labels like noun subjects and direct object can be interchangeably used for semantic roles such as arg0 and arg1. In terms of this mapping between syntax and semantics, AMR is not exceptional, since it utilizes predicate frames from prop bank. One thing we observed is that this statement holds to be true for simple sentences, which is basically a matrix clause comprised of a predicate and its arguments. However, this may not always be the case with complex sentences, each of which consists of not only a matrix clause, but also one or more subordinate clause, usually with a subordinator introducing the subordinate clause. Take a look at the example for as long as construction, where V1 and S1 each stand for the predicate and its subject of a matrix clause, and V2 and S2 consists a subordinate clause. While variables S and B's are interchangeable between two representations, the relation between two predicates and also subordinator itself are expressed quite differently. Compared to a uniform structure of simple sentences, there are various types of complex sentence constructions in human language. This makes it challenging for AMR parsers to parse their structures correctly. Below is an output of parsing a complex sentence with a typical parser CAMR along with the correct AMR. In this case, we can see an error at the core part of the graph, where the relation between the predicates are oversimplified. In our paper, we address this problem of dealing with subordinating structure of complex sentences, which has not been much of a concern in AMR framework. The main objective here is to help parsers deal with complex sentences by providing them which type of constructions is in the input sentence in advance. To achieve this, we take a two-step process to capture the core structure of an input sentence as what we may call skeletal AMR, which could be a beneficial indicator of the type of constructions. Our approach can be roughly divided into pattern matching step and semantic disambiguation step. Here is an overview of our proposed system. We will explain each part step by step. In the pre-processing stage, the system parses an input sentence into a universal dependencies format to make it a form of a dependency tree. It then detects and reverses the head-dependent relation of copular structures. This omits redundancies in creating additional dependency patterns for copular verbs as well as normal predicates. In the pattern matching step, our dependency patterns are matched on the tree in naive manner. It retrieves all occurrences of complex sentence constructions from the input sentence. Then the matcher returns skeletal AMRs, as many as pairs of subordinate and subordinate clause found in the input sentence. In this example, it finds one skeletal AMR for sense construction. Please note that at this stage, a skeletal AMR may contain semantic ambiguities of roles. As illustrated, the skeletal AMR of subordinated sense could show either causal or temporal relation. In semantic disambiguation step, we resolve the ambiguity of roles in the skeletal AMR to obtain the final output, which is restored to its original structure. We have manually created a pattern dictionary that includes dependency patterns of complex sentences and their corresponding skeletal AMR. We use the format given in spacey which employs lemma, parts of speech tags, dependency relations, and regex. The dependency pattern in A describes the simplest type of structure in our dictionary. The nodes that are represented as variables S1 and V1 capture a predicate and its argument in a matrix clause, whereas S2 and V2 capture a subordinate clause. Subordinators are basically described as A's, where their lemma forms are given as Q's. Regex operators are used on both nodes and edges to flexibly match possible elements. For example, the dependency relation illustrated with regex between S and V's enables us to handle noun subjects of both the active and passive voice. At the moment, the number of entries in the dictionary counts up to a total of 70 patterns, including constructions involving degree and quantity, which had been introduced to the latest version of AMR annotation. We also make it available to add new patterns to the dictionary for further expansion. Some subordinators could present ambiguous relations. For such entries, rather than just enumerating entries for each causal or temporal relation, we define a primitive structure of skeletal AMR and disambiguate it in the later stage. It's more practical for our naive matching approach, since it minimizes the size of our pattern dictionary. In the following step, the system resolves ambiguous skeletal AMRs. The disambiguation task can be regarded as a multi-class sentence pair classification. In this task, the relation between the matrix clause and subordinate clause of the input sentence will be predicted. Similar to the approach taken in the field of discourse, we fine-tune a pre-trained BERT model to obtain a classifier. We have selected 4 typical classes, including cause, condition, concession, and time, that covers a wide range of ambiguous constructions. In the disambiguation experiment, we use BERT-based uncased model, 5-fold cross-validation, grid search for hyperparameter tuning, and 2 kinds of metrics, namely macro and micro average for evaluation of trained models. We then present 2 methods to obtain the data, which will be in the form of subordinate clause, matrix clause, a subordinator, and a label. Our first data is called AMR data. It is a supervised data derived from the latest AMR corpus. Another data we use is called Wiki data. This one is a weekly supervised data derived from Wikipedia. In order to obtain this data, we only extract sentences with unambiguous subordinators. For example, we use unambiguous subordinator because for cause and if for condition. In our experiment, we compare 4 kinds of conditions. For 1 to 3, we compare how the difference of training data affect the performance. For 4, we take pre- and post-fine-tuning approach with different datasets under our hypothesis that pre-fine-tuning on wiki data would make BERT model more fit to our task than the original model. We choose BERT AMR model as our baseline. In addition to this, we make modification on softmax layer to take advantage of the information of subordinators in our data. In other words, restrictions are applied to only look at probabilities of relevant classes. For example, when predicting the relation of subordinator since, we make the model to only compare cause and time, ignoring irrelevant condition and concession. We call them restricted softmax models in contrast to vanilla models. Looking at the performance of our vanilla models, training on wiki data by itself does not improve the baseline. BERT Wiki AMR model achieves the highest score among all approaches. This suggests that Wikidata adjusts the pre-trained BERT model to predict sentential relations, which may have boosted the performance of further fine-tuning on AMR data. Pre-fine-tuning on larger weakly supervised data may be an effective option when we have a supervised data of a small size. If we look at the performance of the restricted models, the scores prove that this modification is effective on any of our models, with approximately 3% of improvement each. To sum up our paper, we proposed a pattern matching approach to retrieve complex sentences. We then created a comprehensive dictionary of complex sentence constructions, which contains pairs of dependency patterns and skeletal AMRs. Finally, with the supplemental usage of weakly supervised data, we established a novel baseline for semantic disambiguation of complex sentences in AMR framework. Future work will incorporate skeletal AMRs in AMR parsers. Here are the references for the slides. And this is all. Thank you for listening.